so let's do an experiment that uses the wheel sensor. And so I'm just going to select it over here on the sensor selector, and I'm just going to say record. And I've just made a ramp here with this old shelf I found at the back of my office, and I'm just going to let this thing go. And it rolls down with a constant acceleration. And so anything that moves with constant accelerations, the students study, and they understand that the velocity increases linearly with time, which is what you see right here. And this thing has a constant slope. So for example, if I do an analysis using the software by selecting a region, it tells me what the slope is, and it tells me it's a straight line fits this very well because the correlation coefficient is 0.99. And you can also see by looking at the acceleration at the same time what the acceleration value is. It's about 1/4 meter per second squared. You can zoom in a little bit and you can see that on average. And then if you look carefully up here at the position versus time, you see that that's quadratic, which is what it should be for something with constant acceleration. So you can also do rotational kinematics in a kind of a neat way. In fact, we can use the same setup. Let's use the book again. Here it is. And so it just turns out, by happy coincidence, I wish I could say I designed this on purpose, but I didn't, but an empty this masking tape roll, cardboard roll, fits perfectly and very nicely on one end if you don't push it past the little feet on this thing. So just by putting 2 of these masking tape rolls on it, it rolls beautifully. And so now you can do experiments where, for example, you can do energy conservation of something going down a hill. My students use this to figure out the moment of inertia of this thing, because they figure out MGH and they can figure out the kinetic energy, and from that they can work backwards to find the moment of inertia. So just to do that experiment really quickly, if we go to the gyroscope, which measures rotation rate, and we just let this thing go, there it goes. And we just look at the rotation around the y-axis. So we see that that increases linearly. And if you actually look at the slope of this thing, the slope here is 7 radians per second squared. You get alpha. And so you can even do things like torque equals I alpha experiments by, one of my students actually thought of this. This might be one of the things that I didn't think of that I thought was very clever. So they measured the force that you get from these felt pads on the bottom, and they gave the thing a spin like this. So let me do that experiment for you. If I just measure the gyroscope and I give this thing a spin, like that, you see here that when I zoom in, actually, let's bring this there, and we zoom now. There it is, and we just look at the rotation in the z direction around the z-axis. This thing has a constant rate of change of angular velocity in the z direction, so that means that the angular acceleration, if you do the analysis right there, is fairly constant. And so, because torque equals I alpha, that must come from some torque. And in fact, if you use just sliding it on the table to figure out the coefficient of friction between these felt pads and the table, which you can easily do, that's what the students are doing next week in Physics 101, and you figure out the lever arm from the center out to where each of these pads is, then you can figure out what the force is by each of those pads as it spins, so you can figure out the torque, and you find and you use that measurement of angular acceleration, and you can work out the moment of inertia of this thing around that axis, and you actually get the right answer, which is pretty cool.